Hi, my name is Eric Foley, and this is my Lab 13 video report. In this lab, we had to choose whatever we wanted to do, and I chose to model the motion of a empty can of Coke rolling down an incline. So my objective was to write code to model that, and then use the energy principle to graph what's happening to the energy of the can in the system. My result is that I was able to write code that very accurately modeled the can rolling down the incline. The video I took is in Tracker here. So the can starts at the top and rolls down, and I followed it with the point mass all the way down, and I had it so it ended with a Y value of 0 and started with a Y value of 0.162. This way I could more easily calculate the gravitational potential energy. Also have the axes set up so that the can is rolling in the negative Y direction and the negative X direction. Before I put everything into Python, I decided to calculate some things on paper because I wasn't sure how to use cosine and sine and diagrams in Python. So here is my diagram of the can rolling down the incline, and I got the height and width from the difference in X and Y in the Tracker video, and then the theta that's up there I found by theta is equal to the inverse tangent of the width over the height, and I got that theta is 78.354 degrees. And then from that I found that F normal, which is the force perpendicular to the surface, is the same as the negative sine of theta times the force of gravity, and that's the magnitude of the normal force and the gravitational force. And then sine of theta is 0.9794, so it's negative 0.9794 times the force of gravity. And then from there, since I had to enter a vector as a force for the normal force, I had to find the X and Y components of the normal force. So that came out to be, for X, multiplying it by the sine of 90 minus theta and the cosine of 90 minus theta for the Y component. And then I found what that sine and cosine value were. So then when I put these into Python, I can put the actual decimals and numbers in, so I don't have to use cosine and sine. I also decided to try to find the final velocity outside of Python using the energy principle. So since the can and the Earth are both in the system, delta E equals 0, and you can follow my calculations to see that when I combine the change in gravitational potential energy and the change in kinetic energy with the can at 0 height at the end and with 0 kinetic energy in the beginning, I came down to the conclusion that the final velocity is the square root of 2 times g times h initial, and that came out to about 1.7 meters per second. So here's my code. At the top you can see that the starting position is 0.1620, so that's the same as where it started in Tracker, and I have my g value, and I have the initialization of the potential gravitational energy, which is the mass of the ball times g times ball dot position in the y direction, which comes out to just be height. And then the amount of time that my Tracker video was 0.858 seconds. So my while loop goes for that long. And then within the while loop I have that the gravitational force is equal to the g times the mass of the ball, which is actually the can. And then the normal force, that is the magnitude of the force of gravity times that number, which was the sine of theta that I figured out on the sheet outside of Python on my own. And then the F normal force in vector form is right there with the cosine and sine values that I found on the paper, the 0.2019 and 0.9794. And F net is F graph plus F normal. And then I updated the velocity and position. And then down here I figured out kinetic energy and gravitational potential energy as the for the system, and I had the Earth and the can as the system. So delta E equals 0. So then when I run this code, the orange ball follows the same path that my can did. And then on this graph, the green is the gravitational potential energy and the red is the kinetic energy. So as the can rolls down the hill, the gravitational potential energy approaches 0, and that energy gets converted to kinetic energy. So as you can see, the difference between the red and the green is always the same. So then delta E is 0, staying consistent with the energy principle when the Earth and the can are both in the system. The last part of my Python code printed the final position and the final speed or velocity of the can. So here I have the final position, negative 0.74, and very close to 0, which is very similar, within 2/100ths of a meter of where my tracker video said it ended. And I found 1.7 meters per second as the final velocity using the energy principle, and with Python I found that it was 1.699, so also very, very similar.